Question 7, there's a little sneaky thing that we can do here because I think a lot of people will say, let's let u equal x. And oops, well, no, that's not. Actually, I think a lot of people might do that, right? Say, let's let u equal x. This is going to be dv is going to be the natural log of 1 plus x dx. Right, so problem number 1, kind of hard to take the antiderivative of natural log of 1 plus x. So that would be a little tough, right? So this wouldn't be a great plan. So then second plan might be, okay, well then let's let u equal the natural log of 1 plus x, which means dv would be x dx. Now we have the nice little benefit of taking the derivative of natural log of 1 plus x is relatively easy. It's 1 over 1 plus x. Taking the antiderivative of x dx is going to be x squared over 2. All right, and so then we would kind of multiply these things across, but we'd run into a little bit of a problem, right? We would say this antiderivative is going to be x squared natural log of x over 2 minus the antiderivative of, I'm going to pull that 1 half out, x squared, 1 plus x dx. And although we can actually do this, it wouldn't be with ways that we talked about in class. We could actually do some polynomial long division there and rewrite it and use a partial fraction decomposition. But I don't think that that is what most students would look to do, but that would actually be a thing, right? There are many, many ways of integrating that we did not talk about in class. So what we can do instead here is take advantage of a nice little trick. As soon as it pastes the way that it should, I think I broke Notability. You can't see what my screen says. It's frozen. I should probably pause this. Like, well, nobody wants to hear me talk while it's frozen. Where's my pausing record? All right, so you have no idea how long this thing was frozen for, and it erased everything that it did, which is fine because we don't even need any of this work right here because that's not how we're going to do it. And you can just rewind the video if you want to see how to attack this. So a sneaky thing we can do is we can say something like, let's let a equal 1 plus x, right? This is going to mean that we have the natural log of, sorry, a now. And that also means that, well, x is going to equal a minus 1. So what we would have here, and if we took a derivative, right? So the derivative of x would equal the derivative of a. So what we could do here is we can rewrite this integral as a minus 1 times the natural log of a dA. Why does this help us? Well, now when I take the derivative, when I take integration by parts, if I say u is equal to the natural log of a, and dv is equal to a minus 1 dA, right? My derivative is going to be 1 over a. My antiderivative is going to end up being a squared minus a. So now, when we do an integration by parts, we're going to get u times v, a squared minus a, natural log of a, minus this antiderivative of v du, a squared minus a times 1 over a. You can see where like the magic happens. There's a dA here. So in this integral now, because of our nice, cool, sneaky transformation, we're going to get a squared minus a, which we can divide everything by a minus 1 dA. And the antiderivative of a minus 1, a squared over 2 minus a. We still have this a squared minus a, natural log of a, minus this whole thing, by the way, plus a constant. And then, well, what was a equal to? A was equal to 1 plus x. So we would get 1 plus x squared minus 1 plus x. All of this times the natural log of 1 plus x minus 1 plus x squared over 2 minus 1 plus x plus a constant. And, well, that would be one way that we can write our antiderivative. Damn it, stupid thing. You won't be tested on anything like that bad. Don't even fret one moment.